morning one and all. I am Dr. Ramya Swetha, Civil Engineering Department from Institute of Aeronautical Engineering. Today our topic is hydraulic jump. Coming to the hydraulic jump, these are the web references we are considering for this hydraulic jump. Coming to the hydraulic jump, it is the jump which happened in open channels, the two non-uniform flow. Already we know what is non-uniform flow. Within the length of the channel, the velocity and slope bed, they changes their parameters. So that is called the non-uniform flow. In that non-uniform flow, we already understand in previous videos, we understand the different kinds of flows. Those are supercritical flow, subcritical flow, critical flow. Whenever the critical depth is there, the corresponding flow is known as critical flow. So coming to the supercritical flow, the critical depth is less than the critical depth. Whenever the depth is less than whenever the supercritical flow is happened at that particular point, that particular depth is less than the critical depth, and it is the Froude number is more than 1. Based on the Froude number, we are classifying the critical flows. So Froude number is more than 1. That is supercritical flow. Coming to the subcritical flow, the depth of the whenever the subcritical flow is happening at that particular point, the depth of the subcritical flow is more than the depth of the critical flow. So in that, based on the Froude number is less than the 1. Froude number is less than the 1, and the depth of the subcritical flow is happening that particular point, the depth is more than the critical depth. So these are the parameters we understand in non-uniform flow based on the non-uniform flow. In this, whenever the changes, the unstableness from the unstable supercritical flow to subcritical flow, the transformation, that particular jump is, the whole concept is nothing but the hydraulic jump. Coming to the definition, at the rise of water level which takes place due to the transformation of supercritical flow, that is unstable, to stable subcritical flow. So the complete rise of water level, so that is the jump is known as hydraulic jump. The jump is known as hydraulic jump. So in between, the turbulence flow occurs because of the loss of energy. Because of loss of energy, due to loss of energy. Why? Because the transformation is happening between the supercritical flow to subcritical flow. So this complete, here the turbulence will occur, formations will occur. So the disturbance. So from here to here. Here we are considering section 1.1 and section 2.2. Velocity at respective sections. We are considering velocities at respective sections. The transformation, the rise of water level is nothing but the hydraulic jump. Coming to these hydraulic jump. So already we know it is depends upon the Froude number. Based on the Froude number is more than 1, that is supercritical flow. This depth is less than the critical depth, and this depth is more than the critical depth. This is subcritical flow. The Froude number is less than 1, like this. So whenever the flow is acting like this, coming to this particular section, some particular point on the, whenever we are considering the length of the channel, so here the jump will happen like this. So because of these flow direction and the sudden the rise of the water depth creates some turbulence. So the complete, this is nothing but the hydraulic jump. The hydraulic jump is for understanding. Once you understanding the hydraulic jump, it may helpful for analyzing the different kinds of hydraulic structure. For example, spillways, dams. So these are the examples. So once we understand the hydraulic jump, the analysis and the way of design of parameters also we are going to understanding for hydraulic structure. Now coming to these for understanding the hydraulic jump. So now consider the control volume of water between these two sections. We are considering two sections, section 1-1 and section 2-2. Here from here H1 to H2, in between the hydraulic jump is going to happen. So now consider the control volume of water between these two sections 1-1 and 2-2. Now we are applying the law of conservation of momentum. So now F1 is equal to gamma H1 into 1 divided by H1 by 2. That is equal to gamma H1 square by 2. Where this is nothing but the rho into G. Where gamma is nothing but the rho into G. Where rho is, we know rho is nothing but the density. Rho is nothing but the density. G is the acceleration due to gravity. So now this is the specific weight of water. So gamma is equal to rho into G. Rho is nothing but the density. Similarly for force 2. So F is nothing but the force. Force at section 1-1. From here. The force which belongs to the unstable supercritical flow. So this is the force. So similarly for both, F1 is equal to specific weight of water H1 square by 2. H is nothing but the depth of the water flow at that section 1-1. Similarly for F2, at section 2-2, we are applying the same law of conservation of momentum. So for this also, a force is equal to finally specific weight of water multiplied by H2 square by 2, where H2 is nothing but the depth of the water at section 2-2 at that particular point. So that is subcritical flow condition, stable condition in hydraulic jump. So now horizontal net force F on the control volume. Here we are neglecting the friction effects. Acts backward because H2 is greater than H1. Already we know H2 is greater than H1. It is shown in figure. This H1 and H2. H2 is greater than H1. So because H2 is greater than H1, so neglecting the frictional effects. So the horizontal net force is equal to F1 minus F2. Force at section 1-1 minus force at section 2-2. That gives the net force. So now we know F1 is equal to gamma H1 square by 2 minus gamma H2 square by 2. That is equal to gamma by 2 H1 square minus H2 square. This force is responsible for change of velocity from V1 to V2. This force we have to understand the force which is responsible for the velocity. There is a change in velocity. There is no constant velocity in between section 1 and section 2 in this particular condition. So the force is responsible for change of velocity from velocity at section 1 to velocity at section 2. So this is the condition. Now we know that this force is also equal to the change of momentum of the control volume. So force is equal to mass of water of flowing per second change of velocity. So why? Because in this force the velocity is not a constant one. The velocity varies. Velocity also varies in between the consider whenever we are considering the channel. So in that so force is equal to mass of water flowing per second multiplied by change of velocity. So now force. So now finally what is this? F is equal to gamma Q by G V2 minus V1. This is the thing we have to understand. This is from this change of momentum of the control volume, but based on the change of velocity, force is equal to gamma Q by G V2 minus V1. But we know gamma by 2 H1 square minus H2 square is also the same. So equating those two. Now here we are equating those two equations, those two forces. So by 2 V2 minus V1. The next step is these two are cancelled. Finally, H1 square minus H2 square is equal to, sorry, this is G. This is 2. We know F is equal to gamma by 2 H1 square minus H2 square. Equating these two forces. Now V2 minus V1 is equal to H1 square minus H2 square. So now finally H1 square minus H2 square is equal to 2Q by G V2 minus V1. So from this we may express in different ways based on the requirement. In terms of velocity, in terms of depth of the water depth, like that we may understand this equation. So coming to this H1 square minus H2 square, as from mathematical equation we know, we may write like this also. H1 plus H2 multiplied by H1 minus H2. These two are similar. We may write like this. So now in this equation, H1 square minus H2 square is equal to 2Q by G multiplied by V2 minus V1, that is equal to 2Q by G Q by H2 minus Q by H1, that is equal to 2Q square by G H1 minus H2 by H1 H2. So this is H1 plus H2 H1 minus H2. Cancel these two. So finally H1 plus H2 is equal to 2Q square by G H1 H2. So this is the one kind of formula. We know velocity. From velocity, V2 is equal to V2 minus V1. So coming to the how we will get this from here to here, how we will get. So from velocity Q by H2. Q by H2. This is like this. We are writing like this velocity. We know that is from area is equal to B into H. Q is equal to Q by small q is equal to Q by B. From these, using these equations, finally we will get like this. We are using this terminology. Now, so this is the final one. H1 plus H2 is equal to 2Q square by G H1 H2. Now another one, H2 square plus H1 H2 is equal to 2Q square by G H1. From this to this, we are writing like this. So now from this side we are getting H2 square plus H1 H2 minus 2Q square by G H1 is equal to 0. Based on the mathematical expressions, we may get the quadratic equation after getting all the calculations. Finally, the quadratic equation in terms of H2 is equal to minus H1 by 2 plus or minus root H1 square by 4 plus 2Q square by G H1. This is the equation we will get after quadratic equation calculation. So, we will get this quadratic equation. Solving this quadratic equation, finally, we will get this H2. H2 is equal to minus H1 by 2 plus or minus root H1 square by 4 plus 2Q square by G H1. Here we are considering positive sign, substituting Q is equal to H1 V1. Small q is equal to H1 V1. V1 is equal to Q by H1. This expression already we used in the above equation. So from this, finally H2 is equal to minus H1 by 2. Here we are considering the positive sign only. So square root of H1 square by 4 plus substitute Q with V in terms of V. Now we are getting the equation in terms of velocity, not in terms of discharge per width. This small q already we derived, and is nothing but the discharge per unit width. This is the discharge overall the channel. This is the small q represents the discharge per unit width. So now V1 is equal to Q by H1. Small q is equal to H1 V1. So now H2 in this equation, after getting H2 value in that discharge per unit width, we are replacing with velocity of the flow. So now 2Q H1 V1 square. So root of H1 square by 2 Q square. In that Q we are substituting H1 square V1 square by G H1. Cancel these two. Finally we are getting this equation. Finally we are getting H2 is equal to minus H1 by 2 plus root H1 square by 4 plus 2 H1 V1 square by G in terms of velocity. The depth of the hydraulic jump or the height of the standard wave, the depth of the hydraulic jump is nothing but the H2 minus H1 gives the depth of the hydraulic jump. So like this we are derive the expression. This is the overall expression based on the hydraulic jump. Quick view. So based on the law of conservation of momentum, based on the specific weight of the water, so we are considering the forces with the velocity changes varies from velocities. So from that we are getting this equation. We will get the final quadratic equation, and from that we are substituting the q is equal q in terms of h1 v1. Finally we will get the h2. The depth of the hydraulic jump or height of the standing wave is nothing but the h2 minus h1. Now energy losses due to hydraulic jump. So in between section 1.1 and section 2.2, energy is going to loss. So the difference, the hydraulic jump is the difference between the specific energy heads at section 1.1 and section 2.2. Mathematically, that is nothing but delta E is equal to E1 minus, substitute those specific energy values at respective sections. This is the equation. We will get h1 plus v1 square by 2g minus h2 plus v2 square by 2g. This is the energy loss due to hydraulic jump. This is only for loss of energy due to hydraulic jump, and that is the difference between the specific energies at section 1.1 and section 2.2. Mathematically, this is the expression we will get. So we know the specific energy is equal to h plus v square by 2g. So the relative sections we are applying here simply. So this is the loss of energy loss due to the hydraulic jump. In this hydraulic jump, it's a phenomena that occurs when a fast moving fluid fast moving fluid abruptly slows down and increase in depth, resulting in the turbulent mixing of the fluid. It's a hydraulic jump. It's a phenomenon whenever the flow is going like this, suddenly the fast moving fluid abruptly slow down. The fast moving liquid slow down and increases its depth, resulting turbulent flow. So this is the phenomena we have to understand in the hydraulic jump. We have some key features of hydraulic jump. So in that, the first one is rapid increase in water depth. The rapid increase in water depth, the depth of water increases very highly in a hydraulic jump, and the water level also rises. So the rapid, within the short period, the changes will occur. The water, the flow, the fastness of the flow suddenly it goes to increases within the short length of the channel. The rapid increase in water depth within the small span of the channel. This is the one of the key feature for hydraulic jump. And the next one is energy dissipation. In this, despite the kinetic energy of the fast moving fluid, which is converted into heat, sound and turbulence, in some of the situations we may observe downstream and upstream side of the dams, sudden water will comes and they lift the gates, and in that particular case we are getting some sound, some turbulence we may experience. So that is nothing but based on the hydraulic jump despite the kinetic energy. So the kinetic energy, fast moving fluid. So of the fast moving fluid, so which converted into sound, heat, turbulence. So this is the one more key feature which include in hydraulic jump. And the next one is turbulence. So at fast moving fluid slows down and mixes with slower moving fluid. So the movement and the jump, whenever the hydraulic jump is happening in that particular location, in that particular condition, fast moving fluid slows down and mixes with slower moving fluid. Both are going to mix and turbulence is going to create it. So this turbulence can be seen in the form of different eddies, waves. We may observe in different waves. Eddies, waves, like that we are observing this turbulence. This is the turbulence also one of the important key features in hydraulic jump. Zone of recirculation. Zone of recirculation is also one of the key features. Behind the jump, there is a region where the water flows in a circular motion. This area is called zone of recirculation. Zone of recirculation. Behind the jump, that particular region, whenever the water flows in a circular motion. In a circular motion. Like this. Circular motion. Circular motion. This area is called the zone of recirculation. This is also one of the key features of hydraulic jump. The next one is loss of velocity. Loss of velocity. Why? Because this loss of velocity is happened because of the water decreases. Velocity of the water decreases in hydraulic jump. Water decreases the hydraulic jump, resulting it decreases the rate of flow as well as rate of flow, flow rate or discharge. So this is the one more feature in hydraulic jump, loss of energy. Why? Because the velocity of water decreases in hydraulic jump. The next one is water surface fluctuations. In hydraulic jump, the fluctuations occur in very rapidly, creating waves and disturbances in water. Such kind of phenomena is nothing but the water surface fluctuations. It's completely based on the hydraulic jump. The water surface creates some rapidly creating waves and disturbances in the water. The next one is flow regime. The characteristics of hydraulic jump depend upon the flow regime of the fluid, including its velocity and viscosity. These are the parameters we have to consider, and depends how the hydraulic jump is going to happen, how it is happen, how much length it will get, and how much depth, and all these parameters are including its velocity and viscosity. Overall, hydraulic jumps are important phenomena in fluid mechanics, and they play significant role in various engineering applications such as overall hydraulic jump are important phenomena in fluid mechanics. It plays a very vital role, very significant role in various engineering applications such as dam design. At the time of dam design, it plays a major role. We have to understand all key features in this particular dam design, spillways and water treatment. These are the some of the applications we may apply. We have to understand hydraulic jump. Coming to the efficiency. Hydraulic efficiency, the ratio of the specific energy after the jump to that before the jump is defined as efficiency of the pump. So hydraulic jump efficiency of this is depends upon the specific energy. The ratio of the specific energy after jump to that before the jump is defined as efficiency of the pump. So now E2 minus E2 by E1 based on the Froude number. Based on the Froude number, we are understanding the efficiency based on the Froude number. Now next one is the height of the jump. Height of the jump, the differences between the depths after and before the jump is the height of the jump. The differences here, the specific energy efficiency is specific energy after jump to that before jump. Height of the jump, difference between the depths after and before the jump is the height of the jump. It is also from based on the Froude number. These two expressions are from based on the Froude number. This Hj is nothing but the height of the jump. Height of the jump. E1 is the specific energy at section 1-1. Hj is the height of the jump. Next, coming to the length of the jump. Its length of the jump, so many hydraulic in so many experiments are happened. There is no specific expression for this length of the hydraulic jump. It depends upon the conditions. From coming to the length of the jump, it is different than the efficiency and the hydraulic jump. So the height of the jump. efficiency and height of the jumps are depends upon the parameters are fixed, and we may understand based on that, based on the expressions we may identify. Coming to the length of the jump, it completely depends upon that particular condition, practical particular condition. Coming to the length of the hydraulic jump, as the distance measured from the face of the jump to a point on the surface immediately downstream side of the roller is indicated, which is indicated in figure. This is the length of the jump. This is the length of the jump. These two. This is the height of the jump at section 2-2. This is the height of the jump at section 1-1. This is the velocity of the flow at section 1-1. Velocity of the flow at section 2-2. In between, we are considering the length of the jump. For this, there is no particular expression. Some of the formulas are there based on their interest. So coming to the rectangular, Froude number is more than 10. This is the formula. And Froude number, in some other cases, this is the formula. This is from 1954. This is for 1940. Similarly, in case of these two are for rectangular channel. These two are for rectangular channel. Coming to the trapezoidal channel, we may use this formula. It depends upon the condition and depends upon the type of the channel. So these are the various parameters are depends upon the for understanding the hydraulic jump. And one more, these are the empirical formulas, Cheese's formula, Manning's formulas. So coming to the Manning's formula, this is the formula C is equal to 1 by n, R to the power of 1 by 6. In this, R is the hydraulic radius, n is the Manning's roughness coefficient, and the next one is based on the Cheese's formula. These are the things based in formula. This is the C is equal to 157.6 by 1.81 plus K by root M. Here M is the hydraulic mean depth, K is the Basin's constant. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.